Hello everyone, this is a video lecture for Calculus 3, section 16.4, Green's theorem. Alright, so what is Green's theorem? Let me give you the formula. It is integral over a curve of m dx plus n dy is now equal to the double integral over some kind of domain, an area, of dn dx minus dm dy dA. Okay. Well, there you go. So let's go ahead and start doing some problems here. Essentially, all we're doing is seeing this as two separate pieces with an x and a y, and then we basically, it's kind of like flipping them. You can see the n and the m have switched places, and they have derivatives in not respect to their variable d. Subtract them, and then your area, and it should be pretty easy. So let's do some problems here. Green's theorem is designed, by the way, to make things easier. I'll show you a couple problems where it is easier to do it this way than not. So the very first problem sets us up like this, and they say that this is for the area of a triangle, and they give me 0, 0, 1, 0, and 1, 4. So basically we have a triangle that does something kind of like this up until here 1, 4. Okay, so I need to convert this over. Right here, this is my m, this right here is my n, so I'm going to have double integral of n in terms of x is going to be a 2xy cubed minus m in terms of y is going to be a simple x dA. In order to get this dA to work, we're going to need a line for the top here. Y equals 4x. On the bottom is just going to be a 0, and then 0 to 1 for my limits. 0 to 1 for my x, 0 to 4x of, 2 xy cubed minus x dy dx. All right. To integrate in terms of y, I'm going to add 1 to the power, divide by the new power. Divide by 4 is going to make a 1/2 in the very front. X y to the 4th minus now xy from 0 to 4x dx. Go ahead and distribute that in, or I guess substitute it in is probably a better term for it. 1/2 x 4x to the 4th minus x times 4x dx. Notice that we have a whole lot of 4's going on here. So we got 4 to the 4th, and then divide by 2 is 128. 128 then. Let me go ahead and integrate 0 to 1. 128 x to the 5th, and then minus 4x squared dx. At this point, it's pretty easy. Just add, you could technically use a calculator, but add 1 to the power, divide by that new power, then x cubed over 3 from 0 to 1. Zeros are going to cancel, 1's just make my numbers. Put that into the calculator, and you get a 20 straight up. This particular problem has 2 boxes. They say use Green's theorem, and then don't use Green's theorem. You can put this 20 in both boxes, and it's going to be the same because that's your answer. Okay, next question. 16,409. So integral over a curve, 3y plus 5e to the square root x dx plus, and then I got 8x plus 3 cosine y squared dy. Okay, and it says it's bounded by y equals x squared and x equals y squared. So essentially this x equals y squared is a sideways parabola, and then we got a regular parabola. You can see that we got this section in there. Again, that's going to go from 1 to 1 kind of thing. Well, let's go ahead and find out what we got. So this is my m, and this is my n, and so I'm going to say double integral in terms of, or n in terms of, derivative in terms of x. Yes, it would be an 8, and then here there's no x's at all, so it's just going to be a 0 there, minus, and then my m in terms of the y, I got a 3. Again, no y's there, so it's 0, dA. So 8 minus 3 is simply going to be a 5, dy dx. Now, to be able to get this integral area right here, on my top is the square root, on my bottom is the square, and only the positive square root, 0 to 1. Of course, there's no y's, so you go ahead and add a y. I'll toss the 5 out to the front, so I got square root x minus x squared dx. Again, at that point, you can just pop it in a calculator if you like, but obviously it's just easy integrals from here on out. 2/3 x to the 3/2, and then minus x cubed over 3 from 0 to 1. Putting the 1's in, I get 2/3 minus 1/3. And so ultimately it's 5/3 for your answer. And there you go. Next question, 164011. I'm hoping you're seeing that this is pretty easy. That kind of is the point of this section, is that we're trying to do different styles to make particular problems easier on us. Yet again, we got an m. Here we got an n. So double integral of n in terms of x. The 3 is going to come down to make it 18. Notice that it's a minus sign between them. So might as well see it more so as plus a negative 6. And so my n is going to be a negative. 3 is going to come down to make a negative 18x squared now. Minus, and then m in terms of y. I have my 3 comes down with the 18, and then a y squared dA. Cool. Well, it's kind of interesting with this because you can pull out a negative 18 to the very middle. I'm sorry, to the very front. And now you have this guy here. My area that they're wanting, I forgot to tell you, it's a circle in this particular case. It's a circle, x squared plus y squared equals 4. And I think it's within the circle. So all this area right here. Well, notice that if I'm going to do this circle stuff, I probably want to go to polar mode. And if that's polar mode, r is going to simply equal 2. That's the polar form of that. And so negative 18 can stay in the front. This guy here is technically r squared times, and then r dr d theta. Again, that requisite r you're going to need. 0 to 2, 0 to 2 pi. So that's technically r cubed. So then when I integrate, I'll get r to the 4th over 4 from 0 to 2 d theta. Toss the 2 in. Of course, the 0 is going to cancel. So I got 2 to the 4th power, and then divide by 4. And then I'm going to go ahead and multiply it by the 18. And I got now a negative 72, 0 to 2 pi. I guess you would say like 1 d theta. So put that just 2 pi slide, I guess you can say, or just move the 2 pi down, and so you get negative 144 pi, and that is your answer for that one. Okay, next question. So this one's going to be an interesting one. I want to show you 2 different ways to do it. So in the beginning, they're saying find f dot dr, and that's what they want. But they say to use Green's theorem. Okay, sure. They give me an f is equal to y minus cosine of y, and then x times sine of y. And they want this curve to be within a circle, and then they give me the equation of the circle, x minus 2 squared, and then y plus 8 all squared is equal to 4. And they say it needs to be oriented clockwise. That's going to be an important aspect here in a minute. So what does this look like? Well, 1, 2, 1, 2, 3, 4, 5, 6, 7, 8, way down here, radius of 2. So basically it's kind of like a circle this way, like this. That's pretty close. Remember clockwise, so it's going this way essentially. Okay, I have just a small little thing. What if I were to not use Green's theorem? And so basically what I would have to do is I'm saying I have f dot dr, right? F dot dr. And so I'd have to create my r, which would be a little weird because it's clockwise and shifted. I'm just going to basically give it to you. I'm going to go ahead and say, before we keep going on this, what I'm doing right now you should not do in the end. I want to prove a point, though, okay? So all this right now that I'm doing, like right here, this is not what you should be doing. But I want to just show you something. What if I didn't use Green's theorem? What would it look like? What if I went back to like 16, 2 and 16, 3 and stuff like that? So dr is going to be r prime, obviously. So we got now a cosine and a sine. Okay. And so trying to put it all together, my integral f dot dr, well, you can see that basically it's a dot product with this guy, and then I've got my original f. But remember how this is, again, x's and y's, and this is technically x and y right here. So everywhere you see an x, you got to put that guy. Wherever you see a y, you got to put that guy. And so I'm going to try to write this a little bit better, as best I can at least. I got -2 sine t minus cosine of 2 cosine t minus 8, comma, 2 sine of t plus 2, and then all this stuff here times the sine of 2 cosine t minus 8. Okay, cool. And then all that dot, and then I've got to do my 2 cosine t, 2 sine t dt. Look at this. Cosine of 2 cosine t, blah, blah, blah. It is a mess. That is a mess. You do not want to mess with that, honestly. So is that possible that you could do that, 0 to 2 pi? Sure, I guess. But I'm not going to touch that. So let's just go down. I'm going to try the Green's theorem instead. And so notice here that my f, now this is the good stuff, this is what you should be doing, is basically m and n in that format. And so then I'm looking at it as integral of, my m is going to be that y minus cosine y dx, and then plus x sine of y dy. So this is what I'm really looking at. Well, Green's theorem says that I could essentially take this derivative in terms of the x, which would just leave sine y, and this derivative here in terms of the y, which would be, well, I guess I got a 1, and then I have here negative cosine. The derivative should be a positive sign, actually, and then dA. Well, notice here that when I distribute my negative sign, I'm going to have my signs actually cancel out, and so I have a negative 1 dA, and I'm looking for the area of that circle. So like -1 times, well, I mean pi r squared essentially. That's what this whole double integral dA is, just an area. Well, pi times r was a 2 squared, and so essentially we got, sorry, that square's in the wrong place. It should be right there. And so essentially I got -4 pi. Well, their answer is 4 pi instead of -4 pi. And again, I'm pretty sure the reason why is because we were oriented clockwise. Normally we go counterclockwise, and so I just say, oh yeah, area and all this stuff, and we're good. Well, here notice that because we're going backwards, we should probably take whatever I did have and turn it and change its sign in the end, okay? That's my take on it. So could you keep going with your integral and you might be able to figure it out? Yeah, I guess, but I'm just saying, if it's just double integral dA, just go ahead and do the area of a circle here. Very simple. Okay, 16,4,023. So basically that's why we do Green's theorem, because it's easier, especially in the section, and especially when it says use Green's theorem. So use a formula to find the area under one arch under one arch of the cycloid. Now I'm getting interested. What is this thing? X is equal to t minus sine t, and y is equal to 1 minus cosine of t. One arch of the cycloid, what? Well, notice that if I had just sine and cosine like this without like any other numbers inside of there, I'm pretty sure it's going to be 0 to 2 pi. So that's easy enough to go and do. So my area is kind of interesting because this is a new formula for you. I had to go and look this one up. Is integral of x dy is also equal to the negative integral of y dx, which is also equal to the half integral of x dy minus y dx. Now you can see the kind of the greens part of this, and I'm going to take this one in particular because, I mean, either one of them is fine, but I'm just going to use that because it looks pretty cool. So 1/2 0 to 2 pi, and so then I have x dy, so I got my x, and then my dy, what's my derivative? Like c y prime dy? My derivative here would be just the sine t dt, correct? And then my x prime here, or dx, whatever you want to call it, would be a 1 minus, a negative sign goes to a positive cosine. Again, dt. You don't have to say that, but there will be dt's in here eventually. So, trying to write it all out, here we go. My original x times my y prime, or dy. Big minus sign. My y, my original y, times dx. Again, my derivative there. And then all this stuff here is essentially with dt. All right. I think I did one thing wrong. Negative sign should go, derivative should be a negative cosine right there. Sorry about that. Okay, that was my mistake. Okay, keep going. Now, of course, I want to FOIL it and try to make this thing a little bit better. So distribute your sign. So t sine of t, sine squared. When you FOIL this stuff out, notice the minus is still going to be in the front there. That's a cosine squared dt. When you distribute your negative sign to all these guys, I think that the sine and the cosine are going to kind of cancel one another out here in a second. I think I'm putting too many parentheses there. Okay, there we go. Well, this guy right here and this guy here actually should make together a -1. And then it combines with this guy to make a -2, actually. Wait, I think that was supposed to be my equal sign. Okay. So trying to put some stuff together then, I have t sine of t, and then I have a 2 cosine squared t, and I got a -2 dt. And so in order to get this, whoa, why did I get a square right there? Hold on. I don't know why there was a square there. Sorry. See, I've messed up twice on the same problem. Okay, now we're okay. So then whenever I'm integrating this stuff, again, this is 0 to 2 pi, this part is integration by parts, essentially. I'm sure there's a formula for it as well. Cosine is going to be just going to a negative sign, and the 2 is going to get a t, obviously. For the integration by parts, I chose u equals t, so du equals dt. So dv is equal to sine of t dt, and so v would be equal to negative cosine of t. So when you start putting it all together, for this integral right here, uv minus integral of v du. So these guys here. But your integral negative cosine is going to be a negative sign, and 2 negatives are going to make a positive in the end. This guy here should make my negative... I'm sorry, it's going to go to a positive 2 sine. Positive 2 sine t. And then negative 2 t from 0 to 2 pi. The 0 is going to cancel, I think, everything. These guys here, that's 3 sines right there. And so anyways, go ahead and toss in your 2 pi, and a lot of stuff is also going to cancel out, except for right here, because that'll turn into a 1, and then I basically still have the 2 pi. So there's one thing. When I plug it into here, I'll get a 0. And when I plug this in here, I get a negative 4 pi, actually. 2 times 2 pi. Plugging into 0 is going to make everything cancel. So I got 4 pi, and then minus 2 pi is definitely going to be... Oh, I'm sorry. Both of them are negative. Both are negative. Sorry. So it's negative 6 pi. And then putting this together, we get a negative 3 pi. Now, remember what they were asking for in the very end. They were wanting the area. And so maybe I just messed up something small somewhere. Not with a sign, but maybe a setup. But area should be positive in the end, for sure. Notice that I could have chosen another formula for this area. Maybe I didn't orient it correctly. There's a lot of little things that might have happened. Like if I went from... If you see how you got a sine and a cosine with x and y, technically I might not want to go 0 to 2 pi, but maybe negative 2 pi to 0 or something like that, or even 0 to 2 pi. 2 pi to 0, something kind of like that. I'm not entirely sure. I'm going to let it go. Area is positive. There you go. We're done. All right. I think that's it. So I'm going to stop the lecture. Thank you very much. Have a great day.